Hello there, and welcome back to another episode of Physics with William. This is the space where we peel back the layers of the universe's most intriguing mysteries, one idea at a time. Tonight, we're diving deep into a topic that powers much of our modern world but remains shrouded in complexity: nuclear energy. Now, when you hear the words nuclear energy, what comes to mind? Perhaps visions of glowing reactors, or the immense power that lights up cities. Maybe thoughts of the dangerous side effects or catastrophic events like Chernobyl or Fukushima cross your mind. It's a topic that carries both promise and concern, intrigue and fear. But what is nuclear energy really made of? What's at the core of the power that keeps this world turning? And how does something so small, at the atomic level, hold the key to fueling nations? Before we break all of that down, take a moment to think about something personal. Where are you watching from right now? What's the time for you? It's funny how we all live in different time zones, yet time itself is such a powerful force. It moves without regard for our schedules, keeps everything ticking, whether we are ready or not. And in the same way, nuclear energy is a force of nature that moves quietly, but powerfully through our lives, whether we fully understand it or not. If you find this journey into the world of nuclear energy fascinating and soothing at the same time, consider liking this video or subscribing to the channel. It helps us grow and continue bringing you more deep dives into the topics that matter. And who knows, maybe you'll learn something that changes the way you think about the world. Let's get started. The story of nuclear energy starts with a small, invisible piece of matter, so small that you can't see it, even under a microscope. It's so tiny, yet it holds an immense amount of potential. To understand nuclear energy, we need to first understand what's happening inside the atom. Nuclear energy is often described as an invisible force, and in many ways that description is more accurate than you might think. We don't see the energy itself, at least not in the way we see a fire burning or a machine running. Instead, we feel its impact through the actions it powers, through the lights that brighten a city at night, the factories that keep production lines moving, and even the medical treatments that save lives. But what exactly is nuclear energy, and how does this unseen force come to life? At its core, nuclear energy comes from one of the smallest building blocks of matter, the atom. The atom, made up of protons, neutrons and electrons, is the very foundation of everything around us. It's hard to wrap your mind around just how small an atom is. To give you some perspective, if you could line up 1 million atoms side by side, they would only span the width of a human hair. And yet, despite its tiny size, the atom holds immense power within. This is where nuclear energy finds its source. We all know the atom as the basic unit of matter, but there's much more happening within that tiny space. When we speak of nuclear energy, we're not talking about the atom as a whole, but the process that happens inside its nucleus, the dense core where protons and neutrons reside. These particles, bound together by a force called the strong nuclear force, are what make the nucleus of the atom stable, or unstable, as we'll see later. The potential energy in a nucleus is far greater than what you would expect. If you could somehow pull apart the nucleus of an atom, you'd release a tremendous amount of energy. This process is known as nuclear fission, and it's the core of nuclear power. But it's not just any random process. This release of energy only happens under the right conditions we have learned to control and harness. Imagine the nucleus of an atom as a tiny, tightly packed ball of energy. This ball, while stable under normal conditions, can be disturbed. When it is disturbed, the nucleus can split apart, releasing an enormous amount of energy in the form of heat. This is the basic principle behind nuclear power plants. They use controlled fission reactions to heat water, creating steam, which then turns turbines to produce electricity. It's a process that sounds deceptively simple, but requires careful control. Now, you might wonder, why go through all this trouble with nuclear energy? After all, there are other simpler ways to generate electricity, burning coal for instance, or using natural gas. But nuclear energy has one major advantage over these other methods. It can produce an incredible amount of energy from a very small amount of fuel. Just a small piece of uranium, for example, can produce as much energy as several tons of coal, and unlike fossil fuels, nuclear energy doesn't produce harmful emissions like carbon dioxide, making it a cleaner alternative for power generation. Of course, there's a lot more to nuclear energy than just splitting atoms. There are risks involved, and many people find the idea of harnessing such a powerful force somewhat intimidating. This fear is often fueled by the catastrophic accidents in history, such as Chernobyl and Fukushima. The idea of nuclear energy being as invisible as it is powerful can make it seem both alluring and dangerous. But like all forms of energy, nuclear energy requires careful management and respect for its potential. At its heart, nuclear energy represents a very unique kind of force, a force that, if controlled and harnessed properly, can be used to power entire cities, fuel scientific research, and even help us treat diseases. But if mismanaged, it can have catastrophic consequences. So, as we explore the core of nuclear energy, we'll take a closer look at how we balance these forces, how we manage the risks, and how we continue to unlock the incredible potential of this invisible power. As we continue this exploration, think for a moment about the energy that powers your own world. How much of it comes from sources like nuclear energy, and how much comes from more familiar methods like electricity generated by wind or solar? The balance is shifting, but understanding the hidden forces behind each form of energy is key to shaping a future where we can harness them wisely. Let's dig deeper into the process that turns this invisible energy into something that can power our world, and begin with the atom itself. The atom is far more than a simple building block. It's a source of potential energy waiting to be unlocked, and understanding how to harness that energy is the first step in understanding nuclear power. At its most basic level, everything around us is made up of atoms. The chair you're sitting in, the air you're breathing, the light from your screen, every single object and substance you encounter in your day-to-day life is composed of these tiny, nearly invisible building blocks. Atoms are fundamental to the makeup of all matter, and in the world of nuclear energy, understanding them is the key to understanding how that energy is unlocked. An atom is made up of three primary particles: protons, neutrons, and electrons. At the centre of the atom is the nucleus, a compact and dense region that contains protons and neutrons. Protons carry a positive charge, while neutrons are neutral. They carry no charge at all. Surrounding the nucleus is a cloud of electrons, which carry a negative charge. These electrons move around the nucleus in orbits, and it's their movement that largely determines how atoms interact with one another. To picture this, think of the atom like a tiny solar system. The nucleus is the sun, and the electrons are the planets, constantly in motion, swirling around the nucleus in specific paths. But unlike planets orbiting a sun, electrons don't travel in neatly defined orbits. Their paths are probabilistic. The exact location of an electron at any given time can't be pinpointed, but we know the region where it is most likely to be found. This makes the atom an incredibly dynamic and, in many ways, mysterious object. Now, when we talk about nuclear energy, we're primarily concerned with the nucleus of the atom. The energy stored in the nucleus is immense, much more than in the electrons that surround it. The protons and neutrons are held together in the nucleus by a force known as the strong nuclear force. This force is incredibly powerful, strong enough to keep protons and neutrons packed tightly together, despite the fact that protons themselves repel each other due to their positive charge. But even this strong nuclear force has its limits. If the nucleus becomes unstable or is disturbed, the energy that holds it together can be released in the form of nuclear energy. Understanding the structure of the atom is important because it helps explain why some elements, like uranium and plutonium, are used in nuclear reactors to generate energy. These elements have large, heavy nuclei, which makes them more likely to undergo a process known as nuclear fission. Fission occurs when a heavy nucleus, such as that of uranium-235, is split into two smaller nuclei, releasing a huge amount of energy in the process. This energy comes from the bonds that hold the protons and neutrons together in the nucleus, and when those bonds are broken, energy is released in the form of heat. The type of atom used in nuclear fission has a lot to do with its nuclear structure. Elements like uranium and plutonium are considered fissile, because their nuclei are unstable enough to undergo fission when struck by a neutron. Other elements, like iron or oxygen, do not undergo fission in the same way because their nuclei are much more stable. This difference in stability is what makes some atoms more suitable for nuclear energy generation than others. In a nuclear power plant, the fuel used in the reactor is typically uranium-235. When the atom of uranium-235 is hit by a neutron, the nucleus becomes unstable and splits apart, releasing energy in the form of heat. This heat is used to produce steam, which in turn drives turbines to generate electricity. The process is controlled carefully so that the fission reactions occur in a steady, controlled manner. If the reactions become too rapid, the system can become unstable, which is why controlling the number of neutrons and the rate of fission is so critical in nuclear energy production. This brings us to the concept of nuclear fuel. Unlike fossil fuels like coal, which require vast amounts of material to generate even a modest amount of energy, nuclear fuel is incredibly efficient. A small amount of uranium-235, for example, can generate a tremendous amount of energy. This is one of the reasons why nuclear energy is so attractive. It's capable of producing large amounts of power without the need for vast quantities of raw material. But it also comes with its own challenges, especially in terms of managing the waste produced by the reaction, which we'll explore later. At the atomic level, the potential energy is immense. The reason an atom can hold so much energy is because of the strong nuclear force within its nucleus. This force is one of the four fundamental forces in nature, and it's the key to the power of nuclear energy. But this energy, as we've discussed, is only unlocked under certain conditions that are controlled carefully in nuclear reactors to ensure the process is both safe and efficient. The atom is the foundation of everything, but within it lies an untapped reservoir of energy waiting to be released. The process that allows us to harness this energy, whether it's through fission or potentially fusion, begins with understanding the structure of the atom and the forces that bind it together. From there, we can see how the smallest of building blocks becomes the source of one of the most powerful forces on the planet. As we continue, we'll explore how we take this understanding of atoms and use it to unleash the vast amounts of energy they contain. But before we do, let's take a moment to reflect on just how much the atom shapes the world around us. It's invisible, yet it defines so much of what we experience. It's the engine behind the power we use every day, and it's at the heart of the energy that could fuel our future. So let's dig deeper into how atoms, in their small yet mighty form, can power the world in ways that continue to shape our lives. To truly understand nuclear energy, we need to delve into the structure of the atom, breaking it down to the core of the core. The atom is a tiny, complex entity, composed of three primary components: protons, neutrons, and electrons. Each of these particles plays a unique and crucial role in determining the properties of the atom itself and the energy that can be derived from it. While electrons may steal the show in many chemical reactions, it is the protons and neutrons in the nucleus that are the stars of the nuclear energy story. At the very center of every atom lies the nucleus, a dense cluster of protons and neutrons. Think of the nucleus as the heart of the atom, a compact ball of tightly bound particles that gives the atom its identity. The protons within the nucleus carry a positive charge, while neutrons are neutral. They don't carry any charge at all. Together, these two types of particles make up most of the atom's mass. Surrounding this nucleus are the electrons, which orbit around the nucleus in specific regions called electron shells. Protons are key to understanding not only the identity of the atom, but also its behavior in nuclear reactions. The number of protons in the nucleus determines what element the atom is. For example, an atom with 1 proton is hydrogen, while an atom with 6 protons is carbon. This number, called the atomic number, is a defining characteristic of each element on the periodic table. Neutrons, while they don't contribute to the chemical identity of an element, play an essential role in stabilizing the nucleus. Without neutrons, the repulsive force between the positively charged protons would tear the nucleus apart. Neutrons help balance the forces within the nucleus, keeping the protons together despite their natural tendency to repel each other. The ratio of protons to neutrons in a nucleus can affect the stability of the atom. If an atom has too many or too few neutrons relative to protons, it may become unstable and radioactive. Electrons, on the other hand, are not involved directly in nuclear reactions. They orbit around the nucleus in different shells or energy levels. Their position and energy can determine how atoms interact with each other chemically, but in the context of nuclear energy, their role is less important. What matters more are the interactions within the nucleus, where the protons and neutrons reside. The structure of the atom may seem simple at first glance, but it's the way these particles interact that gives us the extraordinary energy that nuclear reactions can release. When atoms are split, or when their nuclei undergo fission, it's the protons and neutrons that are involved. The electrons, while essential for chemical reactions, don't play a significant role in the release of nuclear energy. At the heart of nuclear power is the concept of nuclear fission, a process that involves splitting the nucleus of an atom into smaller parts. This splitting releases a huge amount of energy as the strong nuclear force that binds the protons and neutrons together is broken. The energy released in this process is what powers nuclear reactors, and it's also the same energy released in atomic bombs. But nuclear fission doesn't just happen by accident. It requires careful manipulation of the atoms, specifically the protons and neutrons, to make it happen. Uranium-235, one of the most commonly used fuels in nuclear reactors, is a perfect example of how the structure of the atom plays a role in nuclear reactions. Uranium-235 has 92 protons and 143 neutrons in its nucleus, which makes it a large and relatively unstable atom. When a neutron strikes the nucleus of a uranium-235 atom, the atom becomes even more unstable and splits, releasing energy. This is fission in action. The energy released in this process is vast because the strong nuclear force holding the protons and neutrons together is incredibly powerful. When this force is disrupted, the energy that was holding the particles together is released. In a nuclear reactor, the process of fission is carefully controlled. The fuel, typically uranium-235 or plutonium-239, is placed in a reactor where neutrons are used to initiate the fission process. The resulting chain reaction releases energy in the form of heat, which is then used to generate electricity. However, to prevent the reaction from becoming too intense, control rods, which absorb excess neutrons, are inserted into the reactor to keep the reaction at a manageable level. It's fascinating to think that the energy needed to power cities, fuel scientific advancements, and even treat diseases all comes from something as small as the nucleus of an atom. The protons and neutrons at the center of the atom are responsible for releasing the vast energy that makes nuclear power such a powerful tool. Yet, this process is incredibly delicate. The balance between protons and neutrons must be just right to ensure that the atom doesn't become unstable. Too many protons or neutrons, and the atom becomes radioactive. Too few, and it can't sustain a fission reaction. The core of the atom is where the magic happens, but it's also where the challenges lie. Understanding how protons and neutrons interact within the nucleus is key to understanding nuclear energy. The energy within an atom's nucleus is not something we can see or touch, but it's there, waiting to be harnessed. And when we learn how to control that energy, we unlock a force that has the potential to shape the world around us in profound ways. So, the next time you hear about nuclear energy, think about the tiny particles, the protons and neutrons at the core of the atom, These seemingly insignificant pieces hold within them the power to change the world, and that's the essence of nuclear energy, an invisible force controlled by the delicate dance of particles that can produce immense power. Fission is the process at the heart of nuclear energy, and it's what allows us to tap into the incredible power locked inside atoms. To understand fission, we need to go back to the basic structure of the atom, particularly the nucleus, which contains protons and neutrons. As we've seen, these particles are held together by the strong nuclear force, a force so powerful that it keeps the nucleus stable under normal conditions. But when an atom is struck by a neutron, this delicate balance can be disturbed, and that's where fission comes into play. In the simplest terms, fission occurs when the nucleus of an atom splits into two smaller nuclei, along with a few neutrons and a tremendous amount of energy. This split happens because the neutron hits the nucleus, causing it to become unstable. The nucleus then breaks apart, releasing a significant amount of energy in the process. The energy comes from the strong nuclear force that holds the protons and neutrons together. When that force is disrupted, the energy stored in the bonds is released, and this energy manifests itself as heat. Fission can occur spontaneously, but it's typically initiated by bombarding the atom with a neutron. The most commonly used element in nuclear reactors for this purpose is uranium-235. Uranium-235 has a relatively large nucleus, making it more susceptible to fission. When a neutron strikes the uranium-235 nucleus, the nucleus absorbs the neutron, becomes unstable, and splits into two smaller nuclei. These smaller nuclei, also known as fission fragments, are usually highly radioactive and unstable. Along with the fission fragments, several neutrons are also released, which can go on to strike other uranium atoms, causing a chain reaction. This chain reaction is the key to harnessing the power of nuclear fission. The neutrons released during fission can collide with other nearby uranium-235 nuclei, causing them to split as well, which releases even more energy and more neutrons. This cycle continues, with each fission event triggering additional fission events, leading to a self-sustaining chain reaction. In a nuclear reactor, this chain reaction is carefully controlled to prevent it from escalating too quickly and becoming dangerous. If left unchecked, the reaction could spiral out of control, releasing an enormous amount of energy in a very short amount of time, as seen in the case of nuclear explosions. To maintain a safe and controlled reaction, nuclear reactors are designed with several mechanisms in place. The uranium fuel is typically arranged in fuel rods, which are placed inside the reactor. These fuel rods are often made of uranium-235 or plutonium-239, both of which are fissile materials. The reactor is filled with a neutron moderator, usually water or graphite, which slows down the neutrons released during fission. Slowing down the neutrons is crucial because fast-moving neutrons are less likely to cause further fission. By slowing them down, the neutrons are more likely to collide with other uranium-235 nuclei and cause further fission events. Control rods, made of materials like boron or cadmium, are also inserted into the reactor to absorb excess neutrons and prevent the chain reaction from becoming too intense. The control rods can be raised or lowered into the reactor to regulate the number of neutrons available to sustain the reaction. By adjusting the position of the control rods, operators can control the rate of fission and maintain a steady, controlled reaction. Once the fission process is underway, the energy released in the form of heat is used to generate steam. This steam is directed to turbines, which spin and generate electricity. The steam is then cooled down and condensed back into water, which can be reused in the reactor. This closed-loop system allows nuclear power plants to produce a continuous supply of energy, which is one of the reasons why nuclear energy is so efficient. A small amount of uranium-235 can produce an enormous amount of energy, far more than could be achieved by burning coal or natural gas. The heat produced by fission can be intense, and the reactors are designed to handle these extreme temperatures safely. They are built with thick, reinforced steel and concrete walls to contain the heat and radiation produced during the reaction. In addition, the reactor is equipped with cooling systems to remove the heat and prevent the reactor from overheating. If the temperature inside the reactor becomes too high, there's a risk of a meltdown, where the core could become damaged and release radioactive materials into the environment. This is why safety measures are of the utmost importance in nuclear power plants. While nuclear fission is incredibly efficient, it also has its drawbacks. One of the most significant concerns is the radioactive waste produced by the process. When uranium-235 undergoes fission, the resulting fission fragments are highly radioactive. These fragments have a long half-life, meaning they remain dangerous for many years, even centuries. Proper disposal and management of nuclear waste is a critical issue, as storing radioactive waste safely requires long-term storage solutions. Additionally, there are concerns about the potential for nuclear accidents, where a failure in safety systems could lead to a release of radiation. Despite these challenges, nuclear fission remains one of the most powerful sources of energy available today. It provides a reliable, consistent supply of energy without the carbon emissions associated with fossil fuels. Nuclear power plants produce a significant amount of electricity with relatively little fuel, and the energy produced by fission can be used to power entire cities. The key to safely harnessing this power is in the careful control of the nuclear reactions that take place inside the reactor. In the end, nuclear fission is a process that represents both the potential and the risks of harnessing the atom's power. It allows us to tap into a vast source of energy, but it also requires strict control, careful management, and constant vigilance to ensure that it remains safe and sustainable. Understanding how fission works is essential to understanding nuclear energy and its role in our future. And as we continue to explore this fascinating field, we'll see how fission is just one part of the puzzle, one that could lead us to even more advanced and efficient energy solutions. Fusion is the process that powers the sun and every star in the universe. It is the ultimate source of energy in the cosmos, a reaction that takes place under extreme conditions of heat and pressure. But could we harness this process here on Earth in a way that's both controlled and sustainable? Could we replicate the sun's power in a laboratory or reactor to provide limitless clean energy? The answer, at least for now, is more of a hopeful maybe than an assured yes. However, understanding the science behind fusion is crucial, as it holds the potential to change how we think about energy forever. To grasp the concept of nuclear fusion, let's first understand what it means to fuse atoms. While fission involves splitting a heavy nucleus into smaller parts, fusion involves combining light atomic nuclei to form a heavier one. It's a process that requires incredibly high temperatures and pressures to overcome the natural repulsion between positively charged protons in the nuclei. This is because protons, being positively charged, naturally repel one another due to the electrostatic force. In order to bring these protons together, they need to be moving fast enough with enough energy to overcome this repulsion and get close enough for the strong nuclear force to take over and bind them together. This process is what happens in the core of stars, including our own sun. In the sun's extreme environment, where temperatures reach millions of degrees, hydrogen atoms are fused together to form helium, a process that releases a massive amount of energy. The energy released in the form of light and heat is what makes the sun shine and what powers life on Earth. This energy is essentially a result of the conversion of mass into energy, as described by Einstein's famous equation, E equals mc squared. The mass of the hydrogen nuclei before fusion is slightly greater than the mass of the helium nucleus after fusion, and the difference is released as energy. In theory, if we could recreate these extreme conditions on Earth, we could harness fusion to produce energy in a clean, efficient, and sustainable manner. The fuel for fusion is typically isotopes of hydrogen, such as deuterium and tritium. Deuterium is abundant in seawater, making it an incredibly sustainable resource, and tritium can be produced from lithium, which is also plentiful. This gives fusion the potential to be an almost inexhaustible source of energy. Unlike fission, which produces long-lived radioactive waste, the byproducts of fusion are far less hazardous. The primary byproduct of the fusion of deuterium and tritium is helium, an inert, non-toxic gas. In this sense, fusion offers a cleaner, safer alternative to other energy sources. However, achieving controlled fusion here on Earth is not a simple task. In the Sun, the extreme temperature and pressure conditions required for fusion occur naturally, but replicating those conditions on Earth is another challenge entirely. In order to initiate fusion, the fuel needs to be heated to temperatures of around 100 million degrees Celsius, 7 times hotter than the core of the Sun. At these temperatures, the fuel is no longer a solid or liquid, but becomes a hot, electrically charged gas known as plasma. Plasma is the fourth state of matter, distinct from solids, liquids, and gases, and it behaves in ways that can be difficult to control. To keep the plasma at these extreme temperatures and pressures, scientists and engineers use powerful magnetic fields to contain it. These magnetic fields are generated by devices known as tokamaks and stellarators, which are designed to create a magnetic cage to hold the plasma in place. The challenge is not just creating these magnetic fields, but also ensuring that the plasma remains stable and doesn't escape or touch the walls of the containment vessel, as doing so would cause the plasma to cool and disrupt the fusion process. For fusion to occur, the plasma needs to remain contained for long enough and at high enough temperatures for the nuclei to collide and fuse. In addition to the technological challenges, there is also the issue of energy input versus energy output. For fusion to be a viable energy source, the energy required to initiate and maintain the fusion reaction must be less than the energy produced by the reaction itself. This is known as the break-even point, and for decades, researchers have struggled to reach it. In the last few years, there have been significant advancements, with some experimental reactors reaching conditions that are closer to achieving this goal, but we are still some distance away from creating a fusion power plant that can produce more energy than it consumes. One of the key advancements in fusion research has been the development of the ITER project in France, a collaboration between multiple countries aimed at building the world's largest tokamak. ITER is designed to demonstrate the feasibility of nuclear fusion as a large-scale and carbon-free source of energy. If successful, ITER could be the first step toward a commercially viable fusion power plant. ITER is not designed to generate electricity, but rather to prove that fusion can be achieved at a scale and efficiency necessary for energy production. If the project is successful, it will provide invaluable knowledge and experience for future fusion power plants. There are also other approaches to fusion research, such as inertial confinement fusion, which uses lasers or other means to compress and heat small pellets of fusion fuel. This method is being explored by a number of private companies and research institutions, and it could offer an alternative path to practical fusion energy. While these methods are promising, they too face significant technological and financial hurdles that need to be overcome before fusion energy can become a reality. So why does fusion remain so elusive, despite its potential to provide clean, abundant energy? The short answer is that the conditions required for fusion are extremely difficult to achieve and maintain, but scientists around the world continue to work tirelessly to solve these challenges, driven by the knowledge that fusion could provide a nearly limitless and sustainable energy source for future generations. It's an energy source that doesn't rely on fossil fuels, doesn't produce harmful greenhouse gases, and has far fewer environmental risks than other forms of energy. The promise of fusion is a world where energy is abundant, clean, and available to all, without the harmful side effects of pollution or resource depletion. In the grand scheme of things, fusion may still be a dream, but it's a dream with the potential to change everything. If we can unlock the secret of fusion, we can not only solve the world's energy crisis, but also take a step toward a future that is sustainable, safe, and clean. The sun's power could be within our reach, and with it, the promise of a brighter, more energy-secure future. As we continue to explore the possibilities of nuclear energy, fusion represents the ultimate frontier, a source of energy that could power humanity for centuries to come. Harnessing nuclear energy is a complex, highly controlled process that transforms the immense power locked within atoms into usable electricity. But to understand how this process works, we need to break down the mechanics of nuclear power generation and how we control the reactions to ensure they are both safe and efficient. From the atoms of uranium to the turbines that generate power, the journey of nuclear energy is a marvel of engineering and scientific precision. At the heart of most nuclear power plants is the principle of nuclear fission, which, as we discussed earlier, involves splitting the nucleus of a heavy atom like uranium or plutonium to release energy. But in order to harness this energy for electricity generation, the fission process must be carefully controlled to produce a steady, reliable source of heat. The process begins with nuclear fuel, most commonly uranium-235. Uranium is mined from the earth and processed into small pellets that are then stacked into long rods. These fuel rods are placed in the reactor core where the fission reaction occurs. The key here is controlling the chain reaction that results from the splitting of uranium atoms. When uranium-235 nuclei undergo fission, they release not only energy in the form of heat, but also several neutrons, which can go on to strike other uranium nuclei, continuing the reaction. This self-sustaining chain reaction is what provides the energy needed for power generation, but without regulation, it could quickly become unstable, even dangerous. To keep the chain reaction under control, nuclear reactors rely on two main strategies: the use of a neutron moderator and control rods. The moderator is a substance that slows down the neutrons produced during fission, making them more likely to interact with the uranium nuclei and continue the chain reaction. In most reactors, the moderator is water, though some reactors use graphite or other materials. Water also plays a secondary role as a coolant, helping to carry away the heat generated by the fission process. Control rods, made from materials like boron or cadmium, are inserted into the reactor core to absorb excess neutrons and prevent the reaction from becoming too intense. By adjusting the position of the control rods, operators can regulate the number of neutrons available for fission, ensuring that the chain reaction continues at a steady, controlled rate. If the reaction begins to speed up too much, the control rods can be lowered further into the core to absorb more neutrons and slow the process down. Conversely, if the reaction needs to be sped up, the control rods can be raised to allow more neutrons to participate in fission. This careful balancing act is what allows nuclear reactors to operate safely and efficiently. Once the fission reaction is underway, the heat generated from splitting uranium atoms is absorbed by the coolant, typically water, which surrounds the fuel rods. The heated water is then pumped through pipes to a heat exchanger, where it transfers its heat to another loop of water. This secondary loop of water is then turned into steam. The steam is directed to turbines, which spin as the steam passes over them. These turbines are connected to generators that produce electricity. Essentially, the process mirrors that of a conventional power plant, where heat is used to create steam, which then drives a turbine to generate electricity. The difference is that, in a nuclear plant, the heat comes from nuclear fission, rather than from burning fossil fuels like coal or gas. Once the steam has passed through the turbines and generated electricity, it is then cooled down and condensed back into water in a cooling tower or heat exchanger. The water is then pumped back into the reactor to be reheated and used again in a continuous cycle. This closed-loop system helps to conserve water and ensure that the reactor operates efficiently over time. The entire process relies on precise engineering and constant monitoring to ensure that everything runs smoothly. Temperature, pressure, and radiation levels are carefully regulated, and backup systems are in place to prevent accidents or malfunctions. In addition to the control rods and coolant, nuclear reactors are designed with thick concrete and steel shielding to protect workers and the surrounding environment from harmful radiation. These shields absorb and deflect radiation, ensuring that it doesn't escape into the atmosphere. Another key component of nuclear energy production is the containment structure. The reactor is housed inside a large reinforced steel or concrete vessel that is designed to withstand high pressures and temperatures, as well as the forces generated during a nuclear reaction. This containment structure acts as the last line of defense in case of a malfunction or accident, helping to prevent the release of radioactive materials into the environment. While the process of harnessing nuclear energy is highly effective, it is not without its challenges. One of the primary concerns with nuclear power is the management of radioactive waste. The fission process produces not only energy but also radioactive byproducts, which remain hazardous for thousands of years. These byproducts are typically stored in special containment pools at the nuclear plant or in dry casks, where they are kept in a safe, secure environment until a permanent disposal solution can be found. Storing and managing nuclear waste is a critical issue, and efforts are ongoing to develop long-term storage facilities, such as deep geological repositories, where the waste can be safely buried and isolated from the environment. Despite these challenges, nuclear energy offers several significant advantages over other forms of power generation. One of the main benefits is that it produces a large amount of energy from a small amount of fuel. While fossil fuel power plants require vast quantities of coal or natural gas to generate electricity, a nuclear plant can generate much more electricity with far less fuel. This makes nuclear energy an efficient and reliable source of power, especially in regions where fuel resources are limited. In addition, nuclear energy produces very little greenhouse gas emissions. Unlike coal, oil, and natural gas, which release carbon dioxide and other pollutants into the atmosphere when burned, nuclear power plants do not produce significant amounts of carbon dioxide. This makes nuclear energy a cleaner alternative to fossil fuels, which contribute to climate change. As the world works to transition to cleaner energy sources, nuclear power is increasingly seen as a viable option for meeting the growing demand for electricity while reducing carbon emissions. Of course, the challenges of nuclear energy, particularly safety and waste management, must be carefully addressed. But as technology advances and our understanding of nuclear physics improves, nuclear power has the potential to become an even more efficient, sustainable, and safe energy source for the future. The key to harnessing nuclear energy effectively lies in careful design, strict safety protocols, and ongoing research to develop better methods for managing waste and minimizing risks. As we continue to explore the world of nuclear energy, we see that the process of harnessing this power is a remarkable feat of science and engineering. From the fuel rods in the reactor to the steam turbines that generate electricity, every step in the process is carefully calibrated to ensure that the energy released by splitting atoms is used to its fullest potential. It's a process that requires precision, control, and constant innovation, qualities that will continue to drive the future of nuclear energy as we strive to meet the world's ever-growing demand for clean, reliable power. To understand how nuclear energy is harnessed, we need to take a closer look at the materials that fuel the process: uranium and plutonium. These elements are the key to generating the energy that powers nuclear reactors, and they play a central role in nuclear fission, the process that releases the heat used to generate electricity. But not all elements are suitable for nuclear energy production. The unique properties of uranium and plutonium make them ideal candidates for the kind of fission reactions needed in nuclear power plants. Let's start with uranium. Uranium is a naturally occurring element found in trace amounts in the Earth's crust. It is a heavy metal, dense and radioactive, and it exists in several isotopes, which are forms of the same element that have different numbers of neutrons in their nuclei. The most abundant isotope of uranium is uranium-238, but it is uranium-235 that is primarily used in nuclear reactors. Uranium-235 is rare in nature, making up only about 0.7% of all uranium found on Earth, while the rest is mostly uranium-238. Uranium-235 is the key fuel in nuclear reactors because it is fissile, meaning it can sustain a chain reaction when bombarded with neutrons. Uranium-235 is an ideal fuel for nuclear reactors because it can easily undergo fission. When a uranium-235 nucleus absorbs a neutron, it becomes unstable and splits into two smaller nuclei, releasing energy in the form of heat. This heat is used to produce steam, which turns turbines to generate electricity. The process of splitting the uranium atom also releases additional neutrons, which can go on to cause further fission reactions, creating a self-sustaining chain reaction. However, there's a catch. Uranium-235 is not the most abundant form of uranium in nature, so to use it effectively as a fuel, we need to enrich it. Natural uranium consists primarily of uranium-238, which is not as readily fissile as uranium-235. To make uranium suitable for use in nuclear reactors, uranium-235 must be concentrated through a process called enrichment. During enrichment, uranium-238 is separated from uranium-235, increasing the percentage of uranium-235 in the fuel. The higher the concentration of uranium-235, the more efficient the fuel will be in sustaining a chain reaction. This enriched uranium is then formed into fuel rods, which are placed in the reactor core to undergo fission. The fuel rods are surrounded by a coolant, usually water, that carries away the heat produced during fission. The coolant is also used to moderate or slow down the neutrons released during fission, allowing them to more effectively cause further fission reactions. Without this moderation, the neutrons would be too fast to sustain the chain reaction. In addition to uranium, another element that plays a critical role in nuclear energy is plutonium. Plutonium is not naturally abundant and does not exist in large quantities on Earth, but it can be produced from uranium-238 in nuclear reactors. When uranium-238 absorbs a neutron, it transforms into uranium-239, which quickly decays into plutonium-239. Plutonium-239 is also a fissile material, meaning it can undergo fission and release energy when bombarded with neutrons. In fact, plutonium-239 is even more fissile than uranium-235, which makes it a valuable fuel in nuclear reactors. The process of converting uranium-238 into plutonium-239 through neutron absorption is known as breeding. In many nuclear reactors, the production of plutonium-239 from uranium-238 is an important part of the fuel cycle. While uranium-235 is the primary fuel used in most reactors, plutonium-239 can be used as a secondary fuel. This process of breeding plutonium-239 allows nuclear reactors to make use of uranium-238, which would otherwise not be very effective as a fuel. Once plutonium-239 is produced in the reactor, it can also undergo fission, just like uranium-235. In fact, some reactors are specifically designed to use plutonium as a primary fuel, and these are known as fast breeder reactors. These reactors are designed to maximize the production of plutonium, which can then be used to fuel the reactor. By using plutonium as a fuel, these reactors can effectively breed more fuel than they consume, which makes them highly efficient and capable of producing large amounts of energy over a longer period of time. The use of plutonium in nuclear reactors, however, comes with some challenges. Plutonium is highly radioactive and it has a long half-life, meaning it remains dangerous for thousands of years. The management of plutonium and its byproducts is one of the major concerns of nuclear energy. In addition, plutonium can be used in the production of nuclear weapons, which raises security concerns. The possibility of plutonium being diverted from nuclear reactors to create weapons has led to strict regulations and safeguards in the nuclear industry to ensure that nuclear materials are not misused. The fuel cycle of uranium and plutonium doesn't end with the use of these elements in nuclear reactors. After the uranium or plutonium has been used in the reactor, it becomes radioactive waste. This waste is highly dangerous and must be handled and stored carefully to prevent harmful radiation from being released into the environment. The management of nuclear waste is one of the biggest challenges facing the nuclear industry today. Spent nuclear fuel is typically stored in cooling pools at nuclear power plants before being transferred to dry storage casks. Eventually, the waste will need to be stored in long-term geological repositories, where it can be safely isolated from the environment for thousands of years. Despite the challenges, uranium and plutonium remain the primary fuels for nuclear energy. These elements are not only capable of producing vast amounts of energy from a relatively small amount of material, but they also offer the possibility of a cleaner, more efficient alternative to fossil fuels. The use of uranium-235 and plutonium-239 in nuclear reactors provides a way to generate large amounts of electricity without the harmful emissions associated with burning coal, oil, or natural gas. And as the world looks for ways to reduce carbon emissions and transition to more sustainable energy sources, nuclear energy, fueled by uranium and plutonium, could play an increasingly important role in our energy mix. So, when we talk about the fuel that powers nuclear reactors, we are talking about two of the most important elements on the planet, uranium and plutonium. These elements are at the core of the nuclear energy process, and understanding how they work, how they are mined, enriched, used, and recycled, helps us better appreciate the complexities and potential of nuclear power. As the world continues to seek cleaner and more efficient ways to generate energy, uranium and plutonium will remain at the center of the nuclear energy conversation, offering both challenges and opportunities in equal measure. Critical mass is a concept at the very heart of nuclear fission, representing the precise amount of fissile material needed to sustain a chain reaction. Achieving critical mass is essential for the controlled release of nuclear energy, whether in a nuclear reactor or a nuclear weapon. The term critical mass refers to the minimum amount of material required to maintain a self-sustained chain reaction, where each fission event causes further fission events, leading to the release of energy. In a nuclear fission reaction, when a fissile nucleus such as uranium-235 absorbs a neutron, it becomes unstable and splits, releasing energy in the form of heat, as well as more neutrons. These neutrons can then go on to cause further fission events, leading to a chain reaction. However, for this chain reaction to continue, there must be enough fissile material present to sustain the process. If there is too little material, the neutrons may escape the system without interacting with other nuclei, and the chain reaction will fizzle out. On the other hand, if there is too much material, or if the reaction is not properly controlled, the chain reaction can escalate too quickly, leading to an uncontrolled release of energy, which can be dangerous. To understand the concept of critical mass more clearly, it's helpful to think of the chain reaction as a kind of feedback loop. When a uranium-235 nucleus undergoes fission, it releases energy and neutrons. If there are enough uranium-235 atoms nearby, those neutrons can strike other uranium-235 nuclei, causing them to undergo fission as well, which releases even more neutrons. This process can continue as long as there is enough material to sustain the chain reaction. The critical mass is the point at which there are enough uranium atoms close enough to each other to ensure that the neutrons released in the fission process will cause further fission events, rather than escaping the system. The critical mass required for a sustained chain reaction depends on several factors. One of the most important factors is the purity of the fissile material. In natural uranium, only about 0.7% of the uranium is uranium-235, with the rest being uranium-238, which is not fissile. This means that in natural uranium a much larger amount of material is needed to achieve critical mass. In contrast, enriched uranium, which has a higher concentration of uranium-235, requires less material to reach critical mass. Plutonium-239, another commonly used fissile material, also has a higher probability of undergoing fission, meaning that less plutonium is needed to reach critical mass. Another important factor is the shape and configuration of the material. fissile material arranged in a compact shape, such as a sphere, is more likely to achieve critical mass because it minimizes the loss of neutrons from the edges of the material. A spherical shape allows neutrons to bounce back and interact with other nuclei, maintaining the chain reaction. In contrast, an elongated or thin shape may result in more neutrons escaping the system, reducing the likelihood of sustaining the reaction. This is why nuclear reactors use carefully designed fuel rods, and why the arrangement of fuel in a reactor is carefully controlled. The density of the material also plays a role in achieving critical mass. The denser the fissile material, the more likely it is that neutrons will collide with other nuclei and cause further fission events. In a nuclear reactor, the fuel is typically packed into fuel rods that are arranged in a grid, ensuring that there is a sufficient concentration of uranium-235 or plutonium-239 in a small area. The presence of a moderator, such as water or graphite, also helps to slow down the neutrons, making them more likely to cause fission. This increases the chances that the chain reaction will continue at a steady rate, rather than dying out or escalating uncontrollably. In a nuclear power plant, the goal is to achieve a controlled chain reaction that produces a steady amount of energy. To maintain this control, the reactor must be carefully monitored, and the critical mass must be adjusted as needed. This is done through the use of control rods, which are made of materials that absorb neutrons such as boron or cadmium. By inserting or removing control rods from the reactor, operators can regulate the number of neutrons available for fission and keep the reaction within a safe range. If the reactor becomes too hot, or the chain reaction becomes too rapid, the control rods can be inserted further into the reactor to absorb more neutrons and slow down the reaction. Conversely, if the reaction needs to be sped up, the control rods can be raised to allow more neutrons to participate in fission. The concept of critical mass is not just important for nuclear reactors, it's also a crucial factor in the design of nuclear weapons. In a nuclear weapon, the goal is to achieve a rapid, uncontrolled chain reaction that releases a massive amount of energy in a very short time. To achieve this, a much larger quantity of fissile material is used, and the material is arranged in such a way that the chain reaction escalates rapidly. This is done by compressing the material into a smaller volume, increasing its density, and ensuring that enough neutrons are present to sustain the reaction. The design of nuclear weapons is highly classified, but it is well known that the critical mass for a nuclear weapon is significantly smaller than for a nuclear reactor. In a weapon, the goal is to reach critical mass almost instantaneously, releasing a tremendous amount of energy in the form of a nuclear explosion. This is achieved through the use of sophisticated engineering, such as the use of conventional explosives to compress the fissile material and achieve the necessary density and configuration for the chain reaction to begin. Once the reaction starts, it accelerates rapidly, releasing an enormous amount of energy in the form of heat, light, and radiation. In nuclear reactors, the critical mass is carefully controlled to ensure that the chain reaction proceeds at a manageable, steady rate. In contrast, in nuclear weapons, the goal is to achieve critical mass as quickly as possible to produce an explosion. The difference in the scale of the reaction and the rate at which the chain reaction occurs is what makes the two applications so different. In reactors, we want to sustain a safe, controlled reaction for long periods, while in weapons, the goal is a rapid, uncontrollable release of energy. The concept of critical mass is one of the most fundamental ideas in nuclear science. It represents the threshold at which a chain reaction becomes self-sustaining, releasing energy that can be harnessed for power generation, or, in the case of weapons, for destruction. Understanding the factors that determine critical mass, such as the type of material, its shape, and its density, helps us design nuclear reactors and manage nuclear fuel more safely and effectively. It also highlights the delicate balance required to control nuclear reactions and the importance of precise engineering and safety measures to ensure that we can harness this incredible energy without it becoming dangerous. Nuclear reactors are fascinating feats of engineering designed to harness the immense power of nuclear fission in a controlled and sustained manner. The concept of splitting atoms to release energy sounds simple in theory, but controlling the reaction to produce a consistent and safe supply of energy is a highly complex and carefully managed process. The challenge lies in controlling something that, in its raw form, is immensely powerful and potentially dangerous. So how do we manage this power safely? How do we tame something as unpredictable as nuclear fission? At the core of every nuclear reactor is the principle of nuclear fission. The fuel, typically uranium-235 or plutonium-239, is placed in the reactor core where fission is initiated by bombarding the atoms with neutrons. Once the fuel begins to split, it releases energy in the form of heat. But while the chain reaction is self-sustaining, it must be kept in check, or the reaction could become too intense, leading to overheating or even a meltdown. The key to controlling the uncontrollable is managing the conditions in which the fission process takes place, and this is where the design of the reactor comes into play. One of the most critical components of a nuclear reactor is the moderator, a substance that slows down the neutrons released during fission. Neutrons that move too quickly are less likely to interact with other uranium or plutonium nuclei, thus slowing or stopping the chain reaction. To ensure that the neutrons move at the right speed, the moderator is used to reduce their velocity, making it more likely that they will collide with other fissile nuclei and continue the reaction. The most commonly used moderators in nuclear reactors are water and graphite. In pressurized water reactors, the coolant is also the moderator, which serves both to transfer heat and to slow down the neutrons. In addition to the moderator, the control rods play a vital role in regulating the chain reaction. Control rods are made of materials such as boron, cadmium or hafnium, which are excellent at absorbing neutrons. By absorbing neutrons, control rods reduce the number of neutrons available to continue the fission process, thus slowing or even halting the reaction when necessary. The control rods are placed in the reactor core and can be inserted or removed to increase or decrease the number of neutrons in the system. By adjusting the position of the control rods, operators can fine-tune the rate of the chain reaction to keep it stable and predictable. The control of the chain reaction doesn't stop with the control rods. The fuel itself is arranged in a way that ensures the reaction remains manageable. The fuel is typically formed into small pellets, which are packed into long metal rods. These rods are then arranged in a grid within the reactor core, ensuring that the uranium or plutonium is spaced out to maintain an even distribution of neutrons. The configuration of the fuel rods, along with the moderator and control rods, creates the conditions necessary for a stable and controlled chain reaction. But even with these safety measures in place, reactors must still be kept at the right temperature and pressure. The heat produced by fission must be removed from the reactor efficiently to prevent it from overheating. This is where the coolant comes in. In most reactors, the coolant is water, which is pumped through the reactor to absorb the heat produced by fission. The heated water is then passed through a heat exchanger, where it transfers its heat to a separate loop of water, which turns into steam. The steam is used to spin turbines, which generate electricity. The coolant is also responsible for maintaining the pressure within the reactor. In pressurized water reactors, the water is kept under high pressure to prevent it from boiling, even at high temperatures. This allows the reactor to operate at a higher temperature and pressure, which increases its efficiency. The pressure in the reactor is carefully controlled to ensure that the coolant remains in a liquid state and that the reactor doesn't overheat. In the event that the temperature or pressure exceeds safe limits, the reactor is designed to automatically shut down to prevent a dangerous situation. The reactor is surrounded by a containment structure, which is designed to prevent the release of radiation into the environment. The containment structure is typically made of thick concrete and steel, which are designed to absorb and block radiation. The structure is also equipped with cooling systems that can remove heat from the reactor in case of an emergency. The containment system is a crucial safety feature, ensuring that even if something goes wrong within the reactor, the radiation is contained and kept away from the outside world. the operation of a nuclear reactor is closely monitored, and numerous sensors and safety systems are in place to ensure that the reactor remains stable. Temperature, pressure, radiation levels, and neutron flux are all continuously measured to ensure that the reactor is operating within safe parameters. If any of these measurements fall outside of acceptable limits, the reactor can automatically shut down or take corrective action to bring it back within safe operating conditions. One of the most important safety systems in a nuclear reactor is the emergency cooling system. In the event of an unexpected problem, such as a loss of coolant or a sudden rise in temperature, the emergency cooling system can rapidly inject water into the reactor to cool it down and prevent a meltdown. This system is designed to kick in automatically if there is any sign of trouble, and it is tested regularly to ensure it is functioning properly. Despite the stringent safety measures, nuclear reactors are not without risks. The most well-known risk is the potential for a meltdown, where the reactor core overheats and the fuel rods begin to melt. This can release radioactive materials into the environment, as seen in the Chernobyl and Fukushima disasters. However, modern reactors are designed with multiple layers of safety features to prevent such an event from occurring. For example, newer reactor designs incorporate passive safety features that rely on natural processes, such as gravity and convection, to cool the reactor in case of an emergency, reducing the need for active mechanical systems. Another risk associated with nuclear reactors is the management of nuclear waste. The fission process produces highly radioactive waste, which remains dangerous for thousands of years. This waste must be carefully handled and stored in secure facilities to prevent it from contaminating the environment. Spent nuclear fuel is typically stored in cooling pools at the reactor site, where it is kept underwater to shield it from radiation. Over time, the fuel is transferred to dry storage casks, which are designed to isolate the waste from the environment. In the long term, the goal is to develop deep geological repositories where nuclear waste can be safely buried and contained for thousands of years. Despite these challenges, nuclear reactors remain one of the most efficient and powerful methods of generating electricity. The ability to control nuclear fission and harness the energy released in a steady, controlled manner is a remarkable achievement in science and engineering. As the world transitions to cleaner energy sources, nuclear power has the potential to play an important role in meeting global energy demands while reducing greenhouse gas emissions. In conclusion, nuclear reactors are marvels of precision and control. By carefully managing the conditions in which fission occurs through the use of moderators, control rods, fuel arrangements, coolants, and containment structures, nuclear reactors can harness the immense power of nuclear fission safely and efficiently. The challenge of controlling the uncontrollable is not just about the science of nuclear reactions, but about the careful design and management of complex systems. As technology continues to evolve, so too will the methods for making nuclear energy safer, more efficient, and more reliable for the future. In the world of nuclear reactors, neutron moderators and control rods are two of the most critical components in ensuring that nuclear reactions proceed safely, efficiently, and at the right pace. While the process of nuclear fission, the splitting of atoms to release energy, is the driving force behind nuclear power generation, it is the careful control of the chain reaction that ensures it happens in a stable, controlled manner. This is where neutron moderators and control rods come into play. They are the instruments that allow us to harness the power of the atom while keeping it from spiraling out of control. Let's begin with neutron moderators. In nuclear reactors, neutrons are the key players in sustaining the chain reaction. When a uranium-235 or plutonium-239 nucleus absorbs a neutron, it becomes unstable and splits, releasing energy and more neutrons. These newly released neutrons can then go on to strike other nuclei, causing them to fission as well. However, for the chain reaction to continue at a steady rate, the neutrons need to be moving at just the right speed. Neutrons that are moving too quickly are less likely to interact with other nuclei and sustain the reaction. On the other hand, neutrons that are too slow may not be able to cause fission at all. This is where the neutron moderator comes in. A neutron moderator is a material that slows down neutrons, bringing them to an optimal speed for further fission reactions. Moderators do not absorb neutrons. Instead, they interact with the neutrons and transfer some of their energy, slowing them down. The goal is to slow the neutrons enough so that they can continue to cause fission events. The most commonly used moderators in nuclear reactors are water, in both pressurized and boiling water reactors, and graphite. Water is the most common moderator, and it has several advantages. Not only does it slow down neutrons effectively, but it also serves as the coolant in the reactor, removing heat produced by fission and transferring it to the steam generators. The use of water as both a moderator and coolant makes it an efficient choice for most nuclear reactors. In addition, water is abundant and relatively inexpensive. However, in some reactors, particularly in older designs or those with higher energy requirements, graphite is used as a moderator instead. Graphite is another excellent neutron moderator, and it has the added benefit of being able to operate at higher temperatures than water, making it suitable for certain reactor types. In the process of slowing down neutrons, moderators play a vital role in sustaining the chain reaction. The energy transferred to the neutrons by the moderator makes the neutrons more likely to interact with other nuclei and cause further fission events. This ability to control the speed of neutrons is crucial to maintaining the balance required for a stable and controlled reaction. Without the proper moderation, the chain reaction could either die out or escalate too rapidly, both of which are undesirable outcomes in a nuclear reactor. Next, we turn to control rods, which work hand in hand with the moderators to regulate the chain reaction. Control rods are made of materials that are excellent at absorbing neutrons such as boron, cadmium or hafnium. The purpose of control rods is to reduce the number of neutrons available for fission by absorbing some of them before they can interact with the fuel. By inserting or removing control rods from the reactor core, operators can regulate the neutron population and adjust the rate of the fission reaction. In a nuclear reactor, the control rods are typically arranged in a way that allows them to be inserted into the reactor core in a controlled manner. When the control rods are fully inserted, they absorb a significant number of neutrons, which slows or even halts the chain reaction. Conversely, when the control rods are withdrawn, fewer neutrons are absorbed, allowing the chain reaction to proceed at a faster rate. By adjusting the position of the control rods, operators can fine-tune the reaction to keep it at the desired level, ensuring that the reactor produces a steady, consistent output of energy. In addition to regulating the rate of the chain reaction, control rods play a crucial role in maintaining safety. In the event of an emergency or an unexpected increase in the rate of fission, the control rods can be quickly inserted into the reactor core to absorb excess neutrons and bring the reaction to a safe level. This is one of the primary safety mechanisms in a nuclear reactor. In modern reactors, control rods are designed to respond automatically to changes in the reactor's conditions. For example, if the temperature or pressure rises beyond safe limits, the control rods can be inserted automatically to reduce the rate of fission and prevent overheating or other dangerous situations. The use of control rods also helps to prevent a runaway chain reaction, which is a potential risk in nuclear reactors. If the chain reaction were to spiral out of control, it could lead to an explosion or the release of harmful radiation. Control rods prevent this by absorbing neutrons and limiting the number of fission events that can occur at any given time. This ensures that the reaction remains stable and does not escalate beyond manageable levels. While the moderators and control rods work together to regulate the chain reaction, they must be carefully balanced to ensure that the reactor operates safely and efficiently. If too many neutrons are absorbed by the control rods, the reaction may slow down too much, reducing the output of energy. On the other hand, if too few neutrons are absorbed, the chain reaction may become too rapid and uncontrollable. This balance is achieved through constant monitoring of the reactor's temperature, pressure, and radiation levels. Operators adjust the control rods and other safety systems to ensure that the reaction remains steady and predictable. In addition to the moderators and control rods, the reactor design itself plays a critical role in controlling the fission process. The arrangement of the fuel rods, the use of reflectors to direct neutrons back into the core, and the design of the coolant system all contribute to maintaining the proper conditions for a stable chain reaction. Nuclear reactors are meticulously designed to prevent overheating, maintain neutron moderation, and ensure that the reactor operates within safe and efficient limits. While the science behind neutron moderators and control rods may seem simple on the surface, it requires precise engineering and constant monitoring. The reactors that power our cities and industries rely on these systems to maintain a safe, controlled fission process that produces the energy we need. The ability to control nuclear reactions has allowed us to harness the power of the atom in a way that is both safe and efficient, at least when done correctly. In conclusion, the role of neutron moderators and control rods cannot be overstated. They are the key mechanisms that allow nuclear reactors to operate safely and efficiently. Moderators slow down neutrons, making them more likely to cause further fission events, while control rods absorb excess neutrons to regulate the rate of the chain reaction. Together, these components keep the reaction under control, ensuring that nuclear energy can be harnessed to meet the world's energy needs while minimizing the risks associated with uncontrolled reactions. As we continue to improve reactor design and safety systems, the role of moderators and control rods will remain central to the operation of nuclear reactors, allowing us to unlock the power of the atom safely and sustainably. Nuclear energy is often viewed through a lens of both promise and fear. On one hand, it offers a clean, efficient source of power with the potential to meet the world's growing energy demands while reducing carbon emissions. On the other hand, the catastrophic events that have occurred in the history of nuclear power, such as Chernobyl, Fukushima, and 3 Mile Island, have left many with a deep sense of unease about the safety of nuclear energy. Understanding how safety is maintained in nuclear reactors and why it is so critical to the operation of nuclear power plants is essential to addressing these fears and ensuring the continued viability of nuclear energy as a power source. At the heart of nuclear safety is the understanding that nuclear reactions, particularly those that occur in reactors, are powerful and potentially dangerous. While the energy released during nuclear fission can be harnessed for electricity generation, an uncontrolled reaction can lead to catastrophic consequences. This is why nuclear reactors are designed with multiple layers of safety measures, all intended to prevent accidents and mitigate risks. The first and most fundamental safety measure is the reactor design itself. Modern nuclear reactors are built with many redundant systems to ensure that, even in the event of an equipment failure, the reactor remains safe. These reactors are designed with a primary safety feature, the containment structure. The containment structure is a thick, reinforced concrete and steel barrier that surrounds the reactor core. This physical shield is designed to contain the radiation and heat generated during the fission process, ensuring that harmful materials do not escape into the environment. The containment structure is one of the most important safety features, acting as the last line of defense if all other safety systems fail. Within the reactor, the fission process is carefully controlled through the use of moderators, control rods, and coolant systems. These components work together to maintain the appropriate temperature and pressure inside the reactor, preventing overheating and ensuring that the reaction remains stable. If something goes wrong and the reactor temperature begins to rise too quickly, emergency cooling systems are activated. These systems inject water or another cooling fluid into the reactor to absorb heat and bring the temperature down to safe levels. In addition to cooling systems, many reactors also use passive safety features which operate automatically and require no human intervention. These passive systems are designed to kick in during emergencies and help prevent accidents. For example, in the event of a power outage or failure of the primary cooling system, many modern reactors are designed to rely on natural forces, such as gravity or convection, to circulate coolant and cool the reactor. This ensures that even if the reactor's active systems fail, the passive safety systems will still work to protect the reactor and surrounding area. Despite these safety features, the public's perception of nuclear energy has often been shaped by the fear of accidents. Events like the explosion at the Chernobyl nuclear power plant in 1986 and the Fukushima disaster in 2011 have left lasting images of nuclear reactors as hazardous and unreliable sources of power. The fear surrounding nuclear energy often stems from the idea that once a reactor reaches a critical point, it can spiral out of control, releasing large amounts of radiation into the environment and causing widespread harm. While these fears are not unfounded, it is important to recognize that the design and operation of modern nuclear reactors have come a long way since those early disasters, and the industry as a whole has learned valuable lessons about safety, transparency, and risk management. Chernobyl remains one of the most well-known nuclear accidents, and its aftermath had a profound impact on the global perception of nuclear energy. The Chernobyl disaster occurred when the operators of the plant conducted a safety test that went wrong, leading to a catastrophic explosion and the release of large amounts of radioactive material into the atmosphere. The accident exposed flaws in reactor design, operator error, and a lack of safety protocols. Since then, the nuclear industry has taken steps to address these issues, implementing more stringent safety regulations, improving reactor designs, and investing heavily in safety culture and training for plant workers. The Fukushima Daiichi disaster, which occurred in 2011, was caused by a massive earthquake and tsunami that disabled the power supply and cooling systems of 3 reactors at the Fukushima nuclear plant in Japan. While the earthquake and tsunami caused widespread destruction, the failure of the reactors was ultimately the result of the plant's inability to withstand such a catastrophic event. Despite the accident, the radioactive releases were relatively low compared to Chernobyl, and the situation was largely contained within the plant's containment structures. Nonetheless, the event reinforced the importance of designing reactors that can withstand natural disasters and of having robust backup systems in place to prevent failure in extreme conditions. In response to these events, the nuclear industry has implemented a number of safety upgrades. For example, reactors today are designed to withstand earthquakes, floods, and other natural disasters. In addition, plant operators are now required to undergo more rigorous safety training and emergency response drills to prepare them for a variety of scenarios, from equipment failures to natural disasters. One of the key lessons learned from past accidents is the importance of having multiple layers of safety and backup systems in place to prevent a single point of failure from compromising the entire system. While nuclear power plants are designed to be safe, they still require constant monitoring to ensure they remain stable and operate within safe parameters. Modern reactors are equipped with a vast array of sensors and monitoring systems that track everything from temperature and pressure to radiation levels and neutron flux. This data is constantly fed to operators who are trained to respond to any anomalies or deviations from normal operating conditions. In addition, nuclear plants are subject to regular inspections and audits by national and international regulatory bodies to ensure they meet stringent safety standards. Another important safety measure in nuclear power plants is the handling and storage of nuclear waste. Spent nuclear fuel, which remains highly radioactive for thousands of years, must be carefully managed to prevent it from posing a danger to human health and the environment. Currently, the most common method for handling spent fuel is to store it in cooling pools at the reactor site, where it is kept underwater to shield it from radiation. Over time, the spent fuel is transferred to dry storage casks, which are designed to safely contain the waste for long periods. In the future, there are plans to build deep geological repositories, where the waste can be stored in underground caverns, isolated from the environment for thousands of years. Despite these precautions, the public's fear of nuclear energy remains a significant challenge. Nuclear accidents, though rare, are high-profile events that capture the public's imagination. The media often sensationalizes the risks associated with nuclear power, and this can lead to widespread anxiety about the safety of reactors and the potential for catastrophic accidents. In order to address these fears, it's important to continue improving safety standards, providing transparent information about the risks and benefits of nuclear energy, and engaging the public in discussions about how to ensure the safe and responsible use of nuclear power. In conclusion, safety is the cornerstone of nuclear energy. While the potential risks associated with nuclear power are real, the advancements in reactor design, safety systems, and operational protocols have made modern reactors significantly safer than their predecessors. The lessons learned from past accidents have shaped the way the nuclear industry operates today, and ongoing improvements in safety culture, training, and technology will continue to make nuclear energy a reliable and clean energy source. However, to fully realize the potential of nuclear energy, we must continue to address public concerns, invest in safety research, and build trust with communities that host nuclear power plants. Only then can we harness the power of the atom in a way that benefits society while minimizing the risks. After the energy is released in a nuclear reactor, there's another important aspect of nuclear power that we must confront: nuclear waste. Unlike other forms of energy generation, such as burning fossil fuels, nuclear energy leaves behind a byproduct that remains hazardous for thousands of years. The question of what to do with this waste is one of the most significant challenges of the nuclear industry. Understanding the nature of nuclear waste, how it's produced, and how it's managed is essential in evaluating the long-term sustainability of nuclear power. Nuclear waste is primarily generated from two sources: spent fuel from nuclear reactors and the byproducts of nuclear reactions. In the case of a nuclear reactor, the fuel that is used, typically uranium-235 or plutonium-239, undergoes fission, splitting into smaller, more stable nuclei while releasing energy. However, the fission process also produces a variety of radioactive byproducts. These byproducts, or fission fragments, are often much more radioactive than the original fuel and can remain hazardous for a very long time. The most common type of nuclear waste is spent fuel, which is what remains after the uranium or plutonium in the reactor has been used up. Spent fuel is highly radioactive and produces a significant amount of heat even after the reactor is shut down. This heat, along with the radiation, makes handling spent fuel a complex and dangerous process. The radioactivity of spent fuel gradually decreases over time, but it can take hundreds of thousands of years for it to become safe to handle without protective measures. Spent fuel is initially stored in large pools of water at the nuclear reactor site. These cooling pools serve two purposes. They provide radiation shielding to protect workers from exposure to harmful radiation, and they help dissipate the heat generated by the spent fuel. The water in these pools is carefully monitored to ensure it remains at the proper temperature, and the spent fuel is typically stored in the pools for several years to allow its radioactivity to decay to a more manageable level. However, cooling pools are a temporary storage solution, and the long-term disposal of nuclear waste requires a more permanent approach. Once spent fuel has cooled in the pools, it is typically transferred to dry storage casks. These casks are made of thick, corrosion-resistant steel and concrete, designed to shield radiation and isolate the waste from the environment. Dry storage is considered a safe and reliable method for storing spent fuel for several decades. However, as the amount of spent fuel accumulates, the need for a long-term storage solution becomes more urgent. One proposed solution for the permanent disposal of nuclear waste is deep geological disposal. The idea is to bury the waste in a stable geological formation, deep underground, where it can be isolated from human activity for thousands or even millions of years. This would prevent radiation from leaking into the environment and ensure that the waste remains contained until its radioactivity is diminished to safe levels. The concept of geological disposal is based on the principle that the Earth's geological formations are capable of safely storing radioactive waste for long periods of time. The waste would be placed in specially designed containers and sealed within deep underground repositories, often in stable rock formations such as granite or clay, which are not prone to natural disasters like earthquakes or volcanic activity. While deep geological disposal is considered by many to be the most viable long-term solution for nuclear waste, it is not without challenges. Finding a suitable location for a permanent repository has proven to be difficult, as many communities are opposed to having a nuclear waste repository built near them. There are also concerns about the potential for groundwater contamination or the possibility of future generations unintentionally discovering and disturbing the repository. As a result, deep geological disposal remains a contentious issue, and many countries are still in the process of selecting sites and developing the technology to make it a reality. In addition to deep geological disposal, there are other methods being researched for dealing with nuclear waste. One such method is reprocessing, which involves chemically treating spent fuel to recover usable materials, such as uranium and plutonium, for reuse in nuclear reactors. Reprocessing can reduce the volume of waste and make better use of the fuel, but it is a complex and expensive process, and it also creates secondary waste that must be managed. Furthermore, reprocessing raises concerns about the proliferation of nuclear weapons, as plutonium recovered from spent fuel can be used in the development of nuclear weapons. Another potential method for dealing with nuclear waste is transmutation, which involves using particle accelerators or reactors to convert long-lived radioactive isotopes into shorter-lived ones. This could reduce the long-term risks associated with nuclear waste, but the technology is still in the early stages of development, and it remains to be seen whether it can be scaled up to a practical, cost-effective solution. In addition to these technological solutions, there is also the issue of public perception and trust. Nuclear waste is often seen as a source of great concern because of the long-lasting dangers it poses. The public fears the possibility of accidents or contamination, and the uncertainty about the safe disposal of nuclear waste has led to widespread opposition to nuclear power in some regions. Transparent communication, public engagement, and careful planning are critical in addressing these concerns and building trust with local communities and the public at large. Without public support, it will be difficult to develop the necessary infrastructure to manage nuclear waste safely. While the long-term management of nuclear waste is a significant challenge, it is not an insurmountable one. With continued research, technological advancements, and careful planning, it is possible to develop safe and effective solutions for disposing of nuclear waste. The need for a reliable and sustainable energy source is more urgent than ever, and nuclear power has the potential to play a key role in meeting that need. However, in order to fully realize the benefits of nuclear energy, we must also address the challenge of waste management and ensure that nuclear power is used responsibly and safely. In conclusion, the question of what to do with nuclear waste is one of the most critical issues facing the nuclear energy industry. While nuclear power provides a clean, efficient source of energy, it also produces waste that must be carefully managed for thousands of years. Current methods of storing nuclear waste, such as cooling pools and dry storage casks, provide short to medium-term solutions, but long-term disposal through deep geological storage remains the most viable option. As research continues and new technologies are developed, the challenge of managing nuclear waste can be addressed in a way that ensures the safety of future generations. It is essential that we continue to find solutions that allow us to harness the power of the atom while protecting the environment and the public from the dangers of radioactive waste. Nuclear energy has long been considered one of the most promising sources of clean, reliable power. As the world grapples with the urgent need to reduce carbon emissions and combat climate change, nuclear energy stands out for its potential to produce large amounts of electricity without the harmful emissions that come from burning fossil fuels like coal, oil, and natural gas. Unlike solar, wind, and hydroelectric power, nuclear energy does not rely on weather patterns or environmental conditions, making it a stable and consistent source of energy. But despite its advantages, nuclear energy has faced significant opposition and scrutiny, particularly due to concerns over safety, waste disposal, and the potential for catastrophic accidents. Still, the promise of clean, abundant energy continues to drive innovation in the nuclear power industry as we search for sustainable solutions to the world's growing energy needs. At its core, nuclear energy offers a unique advantage. It can generate vast amounts of electricity from a relatively small amount of fuel. A single uranium fuel pellet, about the size of a pencil eraser, can produce as much energy as a ton of coal. This high energy density means that nuclear power plants require far less fuel than coal or natural gas plants to generate the same amount of energy, and the waste produced is much smaller in volume. While nuclear waste remains a challenge, the amount of fuel needed to generate electricity is far more compact than that of fossil fuel-based power generation. In addition to its efficiency, nuclear energy produces no direct carbon emissions. Unlike coal or natural gas plants, which release significant amounts of carbon dioxide, CO2, into the atmosphere, nuclear reactors do not produce greenhouse gases during the power generation process. This makes nuclear energy a key player in the fight against climate change, as reducing carbon emissions from the energy sector is essential to meeting global climate goals. The United Nations Intergovernmental Panel on Climate Change, IPCC, has stated that nuclear energy will be a critical component of any effort to limit global warming to 1.5 degrees Celsius above pre-industrial levels. As countries strive to decarbonize their economies and transition away from fossil fuels, nuclear energy has the potential to provide a significant portion of the world's energy needs while helping to reduce emissions. The promise of nuclear energy as a clean energy source is particularly important in the context of the growing global demand for electricity. As the world's population increases and developing nations continue to industrialize, the need for reliable, large-scale power generation is expected to rise dramatically. Renewable energy sources like solar and wind are essential for meeting these needs, but they are often intermittent, meaning they cannot consistently supply electricity when demand is high or when weather conditions are unfavorable. Nuclear energy, on the other hand, provides a steady, reliable source of baseload power that can operate continuously, 24/7, regardless of weather patterns or time of day. Furthermore, nuclear power can complement renewable energy sources in a way that other forms of power generation cannot. As renewable energy technologies continue to advance, nuclear power can play a vital role in ensuring a stable and reliable electricity grid. Nuclear plants can provide the backup power needed when renewable sources like solar and wind are not producing enough energy. For example, during periods of the low sunlight or calm winds, nuclear power plants can step in to provide the electricity needed to keep the grid stable. This ability to provide consistent, dispatchable power makes nuclear energy an essential partner in the transition to a low-carbon energy system. While nuclear energy offers many advantages, there are challenges that must be addressed in order to realize its full potential. One of the biggest challenges is the public perception of nuclear power, which has been shaped by high-profile accidents like Chernobyl, Fukushima, and 3 Mile Island. These disasters have led to widespread fear and skepticism about the safety of nuclear energy, despite the fact that nuclear power plants today are far safer and more reliable than those of the past. Advances in reactor design, safety protocols and regulatory oversight have made modern nuclear plants much less likely to experience a catastrophic failure, but the legacy of these accidents continues to impact public opinion. Another challenge is the issue of nuclear waste. While nuclear power does not produce greenhouse gases during operation, it does produce highly radioactive waste that must be carefully managed for thousands of years. Finding long-term solutions for the safe disposal of nuclear waste is one of the biggest hurdles facing the industry. Currently, spent nuclear fuel is stored in cooling pools and dry casks, but the long-term disposal of waste remains a major concern. While deep geological repositories are considered the most promising solution, political and public opposition to waste storage sites has made progress slow. Despite these challenges, advances in waste management technology and research are underway, and the nuclear industry continues to work towards safe, long-term storage solutions. Additionally, the high upfront costs of building nuclear power plants can be a barrier to their widespread adoption. Nuclear reactors are complex, large-scale facilities that require significant investment in construction, infrastructure, and safety systems, while nuclear power plants can operate for several decades and produce large amounts of energy once built. The high capital costs and long construction times make nuclear energy less attractive in comparison to cheaper and faster to build alternatives like natural gas plants or renewable energy projects. However, as the demand for clean energy grows and the cost of fossil fuels rises, nuclear power may become a more viable option in the long run. Despite these challenges, the promise of nuclear energy remains as strong as ever. As the world seeks to transition away from fossil fuels and reduce carbon emissions, nuclear power offers a reliable, large-scale and low-carbon energy source that can play a crucial role in meeting global energy demands. Advances in reactor design, waste management and safety systems continue to improve the viability of nuclear energy, and new technologies such as small modular reactors, SMRs, offer the potential for safer, more affordable, and more flexible nuclear power plants. SMRs are smaller and less complex than traditional reactors, making them easier and cheaper to build and operate, and they could be deployed in regions or applications where large reactors are not practical. In conclusion, nuclear energy holds great promise as a clean, efficient, and reliable energy source for the future. It offers a solution to the world's growing energy demands while helping to reduce greenhouse gas emissions and combat climate change. While there are challenges that need to be addressed, such as waste management, public perception, and high upfront costs, the potential benefits of nuclear energy make it an essential part of the global energy mix. As we continue to develop safer and more efficient technologies, nuclear power has the potential to play a key role in creating a cleaner, more sustainable energy future. The debate over nuclear energy has been ongoing for decades, and it is one that continues to be deeply divided. On one side, proponents of nuclear energy argue that it's a clean, efficient, and reliable source of power that can help reduce global greenhouse gas emissions and provide the energy needed for a sustainable future. On the other side, critics point to the risks and challenges associated with nuclear power, including the potential for catastrophic accidents, the management of radioactive waste, and the high costs involved in building and maintaining nuclear power plants. The question, then, is whether the rewards of nuclear energy outweigh the risks, or if we are better off relying on alternative sources of energy. To begin, let's look at the rewards of nuclear energy. One of the most significant advantages of nuclear power is its ability to produce large amounts of energy from a small amount of fuel. As we discussed earlier, uranium-235, the primary fuel used in most nuclear reactors, is extremely energy dense. A small amount of uranium can produce as much energy as several tons of coal. This high energy density means that nuclear power plants require far less fuel than fossil fuel plants to generate the same amount of electricity. In fact, the amount of waste generated by nuclear power is much smaller in volume compared to coal or natural gas, making nuclear energy a more efficient option for large-scale power generation. Another key benefit of nuclear energy is its ability to produce reliable baseload power. Unlike renewable sources like solar or wind, which depend on weather conditions, nuclear power plants can operate continuously, 24/7, providing a steady supply of electricity regardless of external factors. This makes nuclear energy a reliable source of power that can help stabilize the grid and ensure that electricity is available when demand is high, such as during peak hours or in the absence of sunlight or wind. Additionally, nuclear energy produces no direct carbon emissions during the generation of electricity, making it a low-carbon alternative to fossil fuels like coal, oil, and natural gas. As the world works to reduce carbon emissions and mitigate the effects of climate change, nuclear energy presents an important solution to help meet global energy needs while reducing greenhouse gas emissions. Perhaps one of the most compelling arguments in favour of nuclear power is its potential to provide clean energy at a large scale. As we transition away from fossil fuels and seek alternatives to reduce the environmental impact of power generation, nuclear energy could play a critical role in meeting the world's growing energy demands. Renewable energy sources like solar and wind are essential, but they are not always available when needed, and they require significant infrastructure to store and transmit electricity. Nuclear power, on the other hand, can provide consistent, high-output electricity, complementing renewable sources and helping to ensure a stable, reliable energy supply. With the growing demand for electricity, driven by population growth, economic development, and the increasing use of electric vehicles, nuclear energy can help meet these needs while reducing dependence on fossil fuels. However, despite these rewards, there are significant risks and concerns associated with nuclear energy, many of which stem from past accidents, the potential for radiation exposure, and the long-term management of nuclear waste. One of the most well-known and catastrophic nuclear accidents in history was the Chernobyl disaster in 1986. A reactor at the Chernobyl nuclear power plant in Ukraine exploded, releasing a massive amount of radiation into the surrounding area. The explosion and subsequent radiation release caused widespread environmental damage, displaced thousands of people, and led to long-term health problems, including cancers and other radiation-related illnesses. Although such accidents are rare, the scale of the disaster left a lasting fear of nuclear energy in the public consciousness. Even though modern reactors are much safer than those of the past, the fear of a catastrophic accident still lingers, particularly in areas with a high population density. Another significant concern is the issue of nuclear waste. As we've discussed, nuclear reactors produce highly radioactive waste, which remains dangerous for thousands of years. The storage and disposal of this waste is one of the biggest challenges facing the nuclear industry. While temporary solutions like cooling pools and dry storage casks are in use, finding a permanent solution for the safe disposal of nuclear waste has proven difficult. Deep geological disposal, which involves burying waste deep underground in stable geological formations, is considered the most promising long-term solution. However, the siting of nuclear waste repositories has faced significant opposition, with communities unwilling to accept the risks associated with having a nuclear waste facility located near them. The long-term management of nuclear waste remains a contentious issue, and without a widely accepted solution, the risks associated with waste disposal continue to be a major drawback of nuclear energy. The high cost of building and maintaining nuclear power plants is another factor in the debate over nuclear energy. Nuclear reactors are complex, large-scale facilities that require significant upfront investment in construction, infrastructure, and safety systems. While nuclear power plants can operate for decades, the high initial cost and long construction time make nuclear energy less attractive compared to other forms of power generation such as natural gas or renewable energy. The cost of decommissioning old reactors and managing nuclear waste adds to the financial burden of nuclear power. While the cost of renewable energy sources like solar and wind has decreased significantly in recent years, nuclear energy has struggled to compete on price, especially given the public's concerns about safety and waste disposal. Moreover, the proliferation of nuclear weapons is an ongoing concern. The technology used to enrich uranium for nuclear power plants can also be used to produce material for nuclear weapons. While strict international safeguards and regulations are in place to prevent the spread of nuclear weapons, the potential for nuclear proliferation remains a risk that cannot be ignored. The development of civilian nuclear energy programs in certain countries may lead to the increased availability of weapons-grade materials, posing a threat to global security. In conclusion, the debate between the risks and rewards of nuclear energy is a complex one, with valid arguments on both sides. On the one hand, nuclear energy offers significant rewards. It is an efficient, reliable, and low-carbon source of power that can help meet the world's growing energy needs while reducing greenhouse gas emissions. On the other hand, the risks associated with nuclear energy, such as the potential for catastrophic accidents, the management of nuclear waste, and the high costs of building and maintaining reactors, cannot be overlooked. As the world seeks to transition to cleaner energy sources, nuclear energy may have a role to play, but its risks must be carefully managed, and ongoing research and innovation are necessary to ensure that it can be harnessed safely and responsibly. As we move forward, it's clear that no single energy source can meet all of our needs. A diverse energy mix that includes renewable sources, nuclear power, and other low-carbon technologies will be necessary to create a sustainable and resilient energy future. The debate over nuclear energy will continue, but with the right safeguards, technology, and public engagement, nuclear power has the potential to be a key part of the solution to our energy challenges. The legacy of nuclear energy is a complex and multifaceted story that spans several decades of innovation, controversy, and reflection. It is a legacy marked by both extraordinary scientific achievement and some of the most devastating disasters in human history. As we look back on the history of nuclear power, it becomes clear that the story of nuclear energy is not just about harnessing the power of the atom. It is also about the impact of this power on society, on the environment, and on global politics. The legacy of nuclear energy is not merely about its technical capabilities, it is about the ethical, political, and environmental challenges that have come with its use, and how we have responded to these challenges. The journey of nuclear energy began with the discovery of nuclear fission in the late 1930s, a scientific breakthrough that opened the door to an entirely new source of energy. In 1938, German scientists Otto Hahn and Fritz Strassmann discovered that when uranium was bombarded with neutrons, it split into smaller nuclei, releasing a vast amount of energy. This discovery led to the development of nuclear reactors, which were first used during the Manhattan Project to produce the atomic bombs dropped on Hiroshima and Nagasaki in 1945. The bombs marked the end of World War II, but they also introduced the world to the immense destructive power of nuclear energy. In the decades following the war, there was a shift in the focus of nuclear energy from weapons to peaceful uses. The 1950s saw the rise of civilian nuclear power, as countries sought to harness the power of the atom for energy generation. The United States, the Soviet Union, and other nations began building nuclear reactors to generate electricity, believing that nuclear power could provide a cheap, abundant, and clean source of energy. The early promise of nuclear energy was immense, an energy source that could power cities, industries, and homes, while avoiding the pollution and carbon emissions associated with fossil fuels. Nuclear power was seen as the key to solving the world's energy problems and ushering in a new era of prosperity. But as the industry grew, so too did concerns about the risks associated with nuclear energy. The first major accident occurred in 1979 at the 3 Mile Island nuclear power plant in Pennsylvania. A combination of mechanical failure and operator error caused a partial meltdown of the reactor, releasing a small amount of radiation into the surrounding area. While the incident did not result in any deaths, it caused widespread public fear and led to a sharp decline in the construction of new nuclear power plants in the United States. The 3 Mile Island accident was a wake-up call, highlighting the potential dangers of nuclear reactors and sparking debates over the safety of nuclear power. The Chernobyl disaster in 1986 further intensified these fears. A reactor at the Chernobyl nuclear power plant in Ukraine exploded, releasing a massive amount of radioactive material into the environment. The explosion and subsequent radiation release caused the deaths of at least 30 people and exposed hundreds of thousands more to dangerous levels of radiation. The disaster also led to the evacuation of over 100,000 people from the surrounding area, and the effects of radiation exposure continue to be felt to this day. the Chernobyl disaster is widely considered the worst nuclear accident in history, and it had a profound impact on the global perception of nuclear energy. It caused many countries to reconsider their reliance on nuclear power and led to a slowdown in the construction of new reactors worldwide. The Fukushima Daiichi disaster in Japan in 2011 was another major event that shaped the legacy of nuclear energy. In this case, a massive earthquake and tsunami disabled the power supply and cooling systems of the Fukushima nuclear plant, leading to the release of radioactive material. While the disaster was caused by a natural disaster, it raised serious questions about the safety of nuclear reactors in the face of extreme events. The Fukushima disaster resulted in the evacuation of over 100,000 people and caused widespread environmental contamination. The global response to Fukushima was swift, with many countries revisiting their nuclear energy policies and, in some cases, shutting down reactors or postponing plans for new plants. These disasters, along with ongoing concerns about the long-term management of nuclear waste, have cast a long shadow over the legacy of nuclear energy. The risks associated with nuclear power, particularly the potential for catastrophic accidents and the challenge of safely storing radioactive waste, have led to a widespread public reluctance to embrace nuclear energy as a long-term solution to the world's energy needs. In many countries, nuclear energy is viewed with suspicion, and the industry continues to face significant opposition, both from environmental groups and from local communities concerned about the risks posed by nuclear reactors and waste storage sites. Yet, despite these challenges, nuclear energy continues to play a significant role in the global energy mix. Today, nuclear power generates about 10% of the world's electricity, and many countries continue to operate nuclear reactors. Some countries, like France, have embraced nuclear energy as a key part of their energy strategy, with over 70% of their electricity generated by nuclear power. Other countries, such as China and India, are investing heavily in nuclear energy to meet their growing energy demands while reducing carbon emissions. The development of new technologies such as small modular reactors, SMRs, offers the potential for safer, more efficient nuclear power generation, and advances in waste management technologies may help address the long-term disposal challenges that have plagued the industry. The legacy of nuclear energy, however, is not just defined by accidents and risks. It is also defined by the scientific and technological achievements that have come from the exploration of nuclear energy. The development of nuclear reactors has led to advances in many fields, including medicine, where nuclear technology is used in imaging and cancer treatments. Nuclear power also played a key role in the space race, with nuclear-powered spacecraft enabling missions to distant planets. The scientific knowledge gained from working with nuclear energy has had far-reaching impacts beyond the power generation industry, shaping fields such as physics, engineering, and environmental science. Looking ahead, the legacy of nuclear energy will likely continue to evolve as new technologies are developed and as the world confronts the dual challenges of meeting growing energy demands and addressing climate change. While nuclear energy is not without its challenges, it remains a vital part of the global energy landscape, offering the potential for clean, reliable power. The lessons learned from past accidents, the advances in reactor safety, and the ongoing research into waste management will play a critical role in shaping the future of nuclear energy. As the world moves towards a more sustainable energy future, nuclear power may play an important role in ensuring that we have the energy we need to power our economies while reducing our carbon footprint. In conclusion, the legacy of nuclear energy is one of both progress and caution. It is a legacy shaped by scientific achievement, but also by the lessons learned from accidents and failures. As we move forward, we must continue to learn from the past, embrace new technologies, and balance the rewards of nuclear energy with the risks it presents. The future of nuclear energy is still unfolding, and its legacy will continue to evolve as we seek to harness the power of the atom in a way that is both safe and sustainable for future generations. As the world faces the challenges of climate change, resource depletion, and the growing demand for energy, the question of whether nuclear energy is the answer to our future energy needs is more pressing than ever. The need for clean, reliable, and scalable energy sources has never been more urgent, and nuclear energy has long been viewed as a potential solution to these challenges. However, despite its many advantages, the future of nuclear power remains uncertain, as it must overcome significant hurdles related to safety, waste management, cost, and public perception. To determine whether nuclear energy is truly the answer, we must consider not only the benefits it offers, but also the challenges it must address. One of the main reasons nuclear energy is seen as a potential key to the future is its ability to provide large-scale, reliable power while producing minimal carbon emissions. As the world moves away from fossil fuels to mitigate the effects of climate change, nuclear energy stands out as a low-carbon energy source. Unlike coal, oil, and natural gas, which release large amounts of carbon dioxide and other pollutants into the atmosphere, nuclear reactors produce no direct carbon emissions during electricity generation. This makes nuclear power a vital tool in the global effort to reduce greenhouse gas emissions and limit the impacts of climate change. Nuclear energy also offers a significant advantage in terms of energy density. The amount of fuel required to produce large amounts of energy is much smaller than that of fossil fuels, and the waste produced by nuclear power is significantly lower in volume. A small amount of uranium or plutonium can generate vast amounts of energy, which makes nuclear reactors highly efficient. This high energy density is particularly important as the world's energy demand continues to rise, driven by population growth, urbanization, and the increasing use of electric vehicles and digital technologies. Nuclear power could help meet this demand while minimizing the environmental impact of energy generation. However, nuclear energy is not without its challenges. The most significant of these challenges is the public perception of nuclear power, which has been shaped by high-profile accidents such as the Chernobyl disaster in 1986 and the Fukushima Daiichi disaster in 2011. These events have left lasting fears about the safety of nuclear reactors, with concerns about the potential for catastrophic accidents, radiation release, and long-term environmental damage. While modern reactors are designed with far stricter safety protocols and advanced technology to prevent accidents, the legacy of these disasters continues to affect public trust in nuclear power. As we move forward, one of the key factors in the future of nuclear energy will be the ability of the industry to rebuild trust, demonstrate safety, and address concerns about the potential risks associated with nuclear power. Another challenge facing the future of nuclear energy is the issue of nuclear waste. The fission process that powers nuclear reactors produces highly radioactive byproducts that remain dangerous for thousands of years. Managing this waste is one of the most pressing issues in the nuclear industry, as the long-term storage and disposal of nuclear waste remain unresolved. While temporary storage solutions such as cooling pools and dry storage casks are in place, there is still no universally accepted permanent solution for the safe disposal of nuclear waste. The development of deep geological repositories, where waste could be stored underground in stable geological formations, is seen as the best option for long-term disposal. However, political opposition and local resistance to siting nuclear waste storage facilities have made progress slow. Until a viable and widely accepted solution for waste disposal is found, the issue of nuclear waste management will remain a major obstacle to the widespread adoption of nuclear energy. The high upfront costs of building nuclear reactors are another challenge. Nuclear power plants are large, complex facilities that require substantial investment in construction, infrastructure, and safety systems. The cost of building new reactors has increased significantly in recent years, partly due to stricter safety regulations and longer construction times. While nuclear power plants can operate for several decades, the high initial costs make nuclear energy less attractive compared to other forms of power generation, such as natural gas or renewable energy, which are often cheaper and faster to deploy. However, as the need for low-carbon energy increases and the cost of fossil fuels rises, nuclear energy may become a more competitive option in the long run. Despite these challenges, there are reasons to be optimistic about the future of nuclear energy. Technological advancements are continually improving the safety, efficiency, and cost-effectiveness of nuclear power. For example, small modular reactors, SMRs, represent a promising innovation in the nuclear energy sector. These reactors are smaller, more flexible, and cheaper to build than traditional large-scale reactors, making them more suitable for deployment in a wider range of locations and applications. SMRs also have inherent safety features, such as passive cooling systems that do not require external power or mechanical systems to operate, reducing the risk of accidents. SMRs could be deployed in remote areas or to supplement renewable energy sources, providing a reliable backup power source for regions with intermittent renewable energy generation. In addition to SMRs, there is ongoing research into next-generation nuclear technologies, such as fast breeder reactors and thorium reactors, which could offer even more efficient and sustainable solutions. Fast breeder reactors are designed to use fuel more efficiently by breeding more fissile material during the fission process, potentially allowing them to operate with much less fuel than traditional reactors. Thorium reactors, on the other hand, use thorium as a fuel source instead of uranium, and they have the potential to be safer and produce less nuclear waste. While these technologies are still in the experimental stages, they offer the potential to make nuclear energy safer, more efficient, and more sustainable in the future. As the world continues to pursue clean, reliable, and sustainable energy solutions, nuclear power will likely remain a part of the global energy mix. Its ability to provide consistent, large-scale power without carbon emissions makes it an attractive option, especially as countries work to meet their climate goals. However, the future of nuclear energy will depend on overcoming the challenges of safety, waste management, and cost. With continued technological advancements, better safety protocols, and improved public engagement, nuclear energy has the potential to play a key role in solving the world's energy problems. In conclusion, nuclear energy is not a perfect solution, but it has the potential to be a significant part of the answer to the world's future energy needs. Its ability to provide clean, reliable, and efficient power makes it an essential tool in the transition to a low-carbon energy future. However, the challenges it faces, particularly regarding safety, waste disposal, and cost, must be addressed in order to unlock its full potential. As new technologies emerge and the global demand for clean energy continues to grow, nuclear power will continue to evolve, and its role in the future of energy will depend on how effectively these challenges are met. Nuclear energy, with its immense potential, holds a dual nature. It has the power to create and sustain, but it also carries the potential to destroy. This duality is at the heart of why nuclear power remains such a complex and often controversial topic. On one hand, nuclear energy can provide a clean, reliable, and efficient source of power, essential for meeting the world's growing energy demands while reducing our reliance on fossil fuels and minimizing the impact of climate change. On the other hand, the very same energy that powers entire cities can also be the source of devastation, as we've seen in the catastrophic events of Chernobyl, Fukushima, and the spectre of nuclear weapons. The power of the atom is a reflection of the complexity and fragility of the world we live in. At its core, nuclear energy is not just a technological advancement. It is a reminder of the responsibilities that come with harnessing such a powerful force. The ability to split atoms and release vast amounts of energy is both a triumph of human ingenuity and a warning about the potential consequences of our actions. The same technology that fuels our power plants and medical advancements can, in the wrong hands or under the wrong circumstances, lead to destruction on a scale we have yet to fully comprehend. As we reflect on the legacy of nuclear energy and look toward the future, we must consider not just the technological advancements and the promise of clean energy, but also the ethical and moral questions that come with it. The challenge is not only to ensure that we can safely harness the energy within atoms, but also to determine how to manage the risks and consequences that come with its use. How do we balance the need for energy with the responsibility to protect the planet and future generations? How do we navigate the complexities of nuclear waste, accidents, and proliferation, while still recognizing the potential of nuclear power to solve some of the most pressing challenges of our time? The future of nuclear energy is not set in stone. It will depend on our ability to innovate, regulate, and most importantly, learn from the lessons of the past. Advances in reactor design, waste management, and safety protocols will be critical in shaping the role that nuclear power plays in the global energy mix. But equally important will be our ability to engage in an open, transparent dialogue about the risks and rewards of nuclear energy, and to build the trust and understanding necessary for its responsible use. In the end, nuclear energy represents both the promise and the peril of human progress. It is a tool that can help us address some of the world's most urgent challenges, providing clean, abundant power while reducing our environmental impact. But it is also a reminder of the profound responsibility that comes with the power to create and destroy. As we move forward, we must strive to harness the power of the atom in a way that benefits humanity and the planet, while always remaining mindful of the potential consequences. The journey of nuclear energy is far from over. As new technologies emerge and as the world's energy landscape evolves, nuclear power will continue to be a central part of the conversation about how we meet the world's energy needs. But as we look to the future, we must always remember that the power to create and destroy lies in our hands, and it is up to us to determine how we use that power